You know, some problems in math just feel impossible, right? They're like these giants that have been standing around for centuries, just daring anyone to even try and solve them. Well, today, we're going to watch one of those giants fall, all thanks to a totally new way of looking at things.
So let's talk about the number 18. What does it actually take to solve an equation to the 18th degree? And I don't mean just getting close, I mean finding the exact answer. For a really long time, the answer was basically, you can't. But yeah, that's about to change.
All right, here it is. Meet our monster. This is the equation we're tackling today, and wow, it's so complex it just looks like a beast, right? With all those terms and coefficients just sprawling across the page. Just to give you a sense of what we're up against, this is an 18th degree polynomial. That's the kind of equation that, historically, was just considered unsolvable if you wanted an exact answer.
I mean, seriously, where do you even start with something like this? Your traditional algebra toolkit, it just falls short. For decades, mathematicians didn't even try for a perfect solution. Instead, they had to settle. They had to settle for an approximation, basically a good enough answer. And that right there leaves us to what I like to call the approximation trap. It's this whole world built on good enough answers, where you have to sacrifice perfect precision just to get any result. But think about it. It feels like physics or engineering, good enough isn't always good enough, is it?
This slide really nails the difference. Think about the classical ways of doing this, like Newton's method. They're kind of like a lockpick. Sure, you can jiggle it around, get really close to opening the lock, but there's always a risk of tiny errors, rounding things off. This new approach we're looking at, it's totally different. It's like having the perfectly cut key, designed from the start to unlock the answer with absolute perfect precision.
So what is this key? Well, it's a powerful new theorem from a mathematician named Ezuidi, and it basically carves a direct path straight to the exact answer, completely bypassing all those old limitations.
Okay, so at its heart, Ezuidi's theorem has a pretty simple goal. Find the exact symbolic roots. Now, what does that mean? It just means finding the actual precise answers. The ones you can write out with symbols like square roots and fractions, not those super long, never-ending decimal approximations. And it gets there using this really clever, step-by-step recursive process. Okay, so here's a look at the engine that drives this whole thing. Now, don't worry, you don't need to memorize this formula. But think of it like this amazing machine. You feed that tangled, messy polynomial into one side, and this recursive process, it acts like a set of gears, just systematically untangling the problem, step by step, until a simple, clean solution pops out the other side. It's pretty incredible.
And the implications of this, they're huge. I mean, this isn't just a new way to calculate something. It directly challenges a really famous mathematical idea called Abel's impossibility theorem. For almost 200 years, everyone just kind of accepted that you couldn't solve general equations of the fifth degree or higher using radicals. This theorem comes along and says, well, actually, it completely redefines what we even consider solvable.
All right, so let's see this thing in action. To solve our massive 18th degree polynomial, the theorem needs to calculate 18 corresponding symbolic coefficients. You can think of these as the building blocks that are going to construct our final exact answer. So the process starts, calculating these coefficients one by one. And right away, a really fascinating pattern starts to emerge. At first, it might seem like nothing's happening, but what the theorem is actually doing is simplifying the problem with every single step.
Okay, first coefficient is calculated, and it's 0.
The second one, also 0.
And believe it or not, this pattern keeps going. The first 8 coefficients, they're all 0. The machine is just elegantly clearing away all the noise and complexity.
And then, bam, we get our breakthrough. The 9th calculation gives us our 8th coefficient, and it is not 0. I mean, look at that. It's a massive number for sure, but it's a real tangible value. This is the first crucial piece of our puzzle.
So, after that big breakthrough, the process continues. And what's really amazing is that the pattern of zeros comes back. Almost all of the remaining coefficients are also 0. This massive simplification, turning what could have been 18 different terms into just a couple, that is the absolute key to cracking this thing. So, after all those calculations, after all those zeros and that one crucial breakthrough, where does that leave us? Well, it's time to reveal the final answer.
Remember that intimidating beast of an equation we started with? You know, the one with 18 different terms? Well, thanks to the incredible simplifying power of all those zero coefficients, it's about to get a major makeover.
And here it is, the elegant result of that whole process. That entire sprawling polynomial just collapses into the simple, clean form. Instead of 18 different terms, now it only depends on x to the 18th power, x to the 9th power, and a constant. All of a sudden, the unsolvable looks, well, pretty solvable, doesn't it?
And with that much simpler equation, we can find the exact symbolic root. Look at this. It's not a long decimal approximation that gets cut off. It's a perfect, precise answer. This is the key that was cut to fit the lock perfectly. It turns the impossible into the solved. So the crucial point to take away is this. We've moved beyond the world of good enough. Azuiti's theorem gives us a level of precision and certainty for these super complex problems that the classical methods, they just couldn't reach.
And that leaves us with a really fascinating thought, doesn't it? If a problem that stood for so long as unsolvable can be so elegantly dismantled with just a new way of thinking, it really makes you wonder, what other mathematical mountains out there are just waiting for the right tool to show us they were really hills all along?